What is the matter composition of the universe? This is the question I'm ambitiously trying to answer using simple math and a model of discrete dimensionality. The majority of all matter in the universe is invisible, which poses a challenge to any complete theory. Let's analyze a potential answer using discrete dimensionality and how it provides a direct explanation for all matter. Let's start with a discrete 1D point of attraction. Here, there are two potential coordinates for movement. It may enter from the right and shift toward the left. For a 2D axis, there are 4 possible coordinates to enter and 3 remaining points of potential. This means that from a 2D point of attraction, there are 4 times 3 is equal to 12 potential coordinates to occupy. With a 3D point of attraction, there are 6 points of entry and 5 points remaining. So a 3D point of attraction offers 6 times 5 is equal to 30 potential coordinates. Now let's analyze the percentage of attraction for all dimensions. 30 plus 12 plus 2 is equal to 44. Here 30 is 3D, 12 is 2D, and 2 is 1D. 3D equals 68%. 2D equals 27%. 1D equals 4.5%. This coincidentally aligns with the observed matter composition of the universe. We only observe 1D attraction. I refer to the strong force as this kind of point, which I will explain further. However, this assumes a static value of dark matter and antimatter. This directly contradicts the Big Bang inflation model, a widely accepted framework, which posits that there is no static total value for dark matter and dark energy. My model instead suggests a beginning of complete homogeneity, with time progressing toward heterogeneity. Rather than a Big Bang, I argue for a model of prior static phase transition, which is mathematically plausible and referenced in related studies. Since there are many intellectuals who also question the inflation model, like Nobel laureate Roger Penrose, for instance, I will continue analyzing with my model. Analyzing problems with the Big Bang and inflation. 1. Fine-tuning. The biggest challenge for the Big Bang model is that it requires stable structures, which demands a perfect balance in the forces of nature. Even a slight offset in these forces would make stable, dynamic structures impossible. 2. Hot, dense state post-inflation. The end of inflation resulted in a very hot and dense state, but it had to be balanced perfectly, either too great nor too low in temperature. This adds to the complexity of the fine-tuning issue. 3. Massive black holes in the early universe. Even with fine-tuning, calculations indicate that black holes in the early universe would be much larger than expected. Analyzing arguments for why the Big Bang model is near perfect. 1. Expansion. Any model needs to explain why the universe is expanding. My theory accounts for this by suggesting there are more 2D and 3D points of attraction, which are ontologically larger. 2. Abundance of light elements. Another argument for the Big Bang is its ability to explain the abundance of light elements. With a prior static phase universe, everything would emerge from a 1D point, enforced by my non-repetition theorem, ensuring the first elements were simple in nature, allowing for chronological order. 3. Homogeneity. The Big Bang model also explains the universe's homogeneity, as illuminated by cosmic background radiation data. My model combines all discrete dimensionalities, eventually evolving into more heterogeneous structures, similar to how mixed oil and water gradually separate. Why can't we see dark matter and dark energy? To answer this, we need a few premises. 1. Non-repetition of information. Repetitive information is impossible, aligning with Heisenberg's uncertainty principle and relativity, without going into the mathematical complexities of information repetition. 2. Equal force for all discrete points of attraction. Every discrete point of attraction exerts an equal force. 3. Photons and dimensional leaps. Photons don't experience space and time from their own reference point. They travel instantly from point A to point B, which is already established. This allows for dimensional leaps via photons. There's also the principle of least action. Leptons as axis transfers. In 3D, there are 6 possible axis points for transfer, aligning with the number of leptons. Antileptons can be explained by axis point exchange. Think of it as a trade, similar to humans exchanging items. Leptons don't experience the strong nuclear force, which aligns with the fact that 3D axis transfers are ontologically not a 1D matter attraction. In 3D, you can trace 2D but not 1D, except in cases of spontaneous alignment. This explains superposition as a defined, though relatively untraceable, unit, addressing Schrödinger's cat paradox. The defined movements from each discrete dimensionality equal 18, which aligns with quarks combined with color charge. In illustrating a helium-4 atom with quantum particles, 1D attraction represents the strong nuclear force, and the lepton would serve as the radiation potential for photons. The electron sits at the outermost layer of an atom, consistent with discrete 3-dimensionality. All matter includes photons to ensure the total structure is defined. Without them, structures become undefined and problematic. I actually predict that protons initially repel the strong nuclear force, but that the overall structure remains one that protons naturally seek. There is a lot more reasoning behind all of this, but I will explain it in greater detail in another video. Potential example of a 2D attraction point. One potential structure here should follow the laws of least action and non-repeatability. I propose that the electron should occupy a 1D coordinate, meaning that photon mediation exists solely in one dimension. From our 3D reference point, this structure appears as a dot, like a spontaneous matter-antimatter collision, explained by vacuum energy and the Casimir effect. It appears that a 3D point of attraction has a stable structure when the electron is at its 1D point, also observable via the Casimir effect. The last part of this video is complex and a work in progress. If you've watched this far, thank you so much for your attention.